Alright, Unit 2 practice exam for Math 1050. Question 1 from section 3.1. Finding the standard form, which could also be called vertex form. Once it's in standard form, we can easily identify the vertex. Sketch the graph would be easier in standard form. So the way this was presented in class is by completing the square. What we're going to do is move that 3 over. And then also factor this 2 out of the remaining 2 terms here. Factor the 2 out of that, which is going to give you x squared plus 4x. And then we have a term here that we need to add to the right side that's going to complete the square. So the little formula that goes along with this is half of b squared, where this is b. So half of 4 is 2. 2 squared is 4. So 4 is the value that completes the square. Now, since this is an equation, whatever we add to the right side, we have to add to the left side. And we've added 2 times 4 here, which is 8. So we've got to add 8 to the left to keep things balanced. So we have f of x plus 5 equals 2, and then x squared plus 4x plus 4 is x plus 2 squared. Now if we take this 5 and subtract it over to the right side, we're going to have f of x equals 2 times x plus 2 squared minus 5. Now that it's in standard form like this, we can state the vertex as the value of those 2 values right there. And since it's plus 2, it's going to move 2 to the left, so the vertex is negative 2, comma negative 5. Now, graphing this, we know that the vertex is 2 to the left, down 5. And because of the 2 being positive leading coefficient, I know this parabola faces up. Want to get the correct shape, this 2 right here, or this 2 leading coefficient makes the graph vertically stretched, so it's a little bit narrower. Or we could also use the Y-intercept here as positive 3, but what I'm going to do is just plug in a value of negative 1 to find out where another point is near the vertex. So if I plug negative 1 into the standard form here, plug in negative 1 for x, right here, I'm going to get negative 1 plus 2, it's 1, 1 squared, it's 1, 1 times 2, it's 2, and then 2 minus 5 is negative 3. So negative 1 comma negative 3 is on the graph, and that point gets reflected on the other side of the vertex. There's a graph of the function. It says state the range. Range is, remember, along the y-axis here, the y values. So looks like the lowest y value is negative 5. The highest y value is going to be positive infinity. Alright, question 2, also from section 3.1. This is an application problem of quadratic functions. Key word here is finding a maximum. We talked about this in class. Whenever, especially knowing that we're dealing with quadratics, it says find the maximum this or minimum that, really it just means to find the vertex. So essentially we're going to be finding a vertex of a quadratic function. What we need to do though is build that quadratic function. So it says there's a rectangular enclosure, make that a little bigger, and it's going to be split into 2 equal parts, and there's 600 feet of fencing available to go around this enclosure, or to enclose the whole thing, including this middle piece. So that's a perimeter. If it's going around the outer edges, that'd be known as a perimeter. So if we label this and measured all around the perimeter, including this middle piece, we're going to have 3x plus 4y equals 600. That's our perimeter. But it's not asking us to find the maximum perimeter. It's asking us to find the maximum area. And the area of this is length times width. So the area is 2y, and then the width is x. Now the problem with this is this area formula here has too many variables. We can't, it's not even a quadratic function at this point, and it's not technically a type of function we want to deal with because it has too many variables. So what we need to do is use this perimeter equation to solve for one of its variables and plug that into the area equation. So what we can do, I'm going to go ahead and erase this area. Let's get rid of that. Here we go. For example, if I subtracted a 3x, or you know what, let's do it this way. Subtract a 4y so now we've got 3x equals 600 minus 4y, and then divide by 3. So x equals 200 minus 4/3 y. So now we know what x equals. X equals 200 minus 4/3 y. Going back to area, area was equal to 2y times x, but knowing that x has this value, I can make that substitution into this area formula where area equals 2y. Rather than multiplying it by x, I can multiply it with this expression, which is 200 minus 4/3 y, which equals negative 8/3 y squared plus 400y. And this is area. This represents area. Now what we have in this equation right here, that's the equation of a quadratic, and since it has a leading coefficient that's negative, if we were to graph that quadratic, it would be facing upside down, and the vertex there would be our maximum value, which is what they're asking us to find, a maximum value. So what we do in this case is use our vertex formula. So the vertex, if you remember from section 3.1, was the opposite of b divided by 2a, where this is b, so that's negative 400 divided by 2 times a, and this is a right here. 2 times that is 2 times negative 8/3. So this is 400 divided by 16/3. Which is, let's see, 1200 divided by 16. I'm getting on a calculator. Get 75. And since this original function here was defined in terms of y, then this is the y value. Y is equal to 75. So halfway there, I know the y value. What I don't know, so I know this is 75. What I don't know is the x value. But I know from this equation that x is 200 minus 4/3 y. So if I know that y is 75, then 4/3 times that, so let's do 4/3, 75, that's 100. If you take that from 200, you get 100. So by plugging in a 75 right here, you're going to get x equals 100. And we know that these are the dimensions that would maximize this area because we found the vertex, and the vertex would be the maximum of that parabola. Okay, question 3, also an application problem from section 3.1. This one may be a little more straightforward because rather than having to build a function, we've been given a function. And it asks us how many seconds it will take for the rock to reach its maximum height. Here's that word maximum. And what is the maximum height? Knowing that we're dealing with, since this parabola faces upside down, we know the vertex is going to be a maximum point. So we're just finding the vertex. So essentially what we're doing is find vertex of the height at any time t so we're going to use the vertex formula. Opposite of b over 2a, the opposite of b is negative 32 over 2 times a, so it's negative 32 over negative 32, which equals 1. And this is in terms of t, which stands for time. So time here is measured in seconds, so I know this is 1 second. So this answers this first question: how many seconds will it take the rock to reach maximum height? It's 1 second. What is the maximum height? Well, this model that was given to us models the height at any time t. And now we have a specific value of t, 1 second. So if I want to find the height at 1 second, I just plug it in to the function itself. So negative 16 times 1 squared is negative 16. Negative 16 plus 32 times 1, that's 32. So negative 16 plus 32, 16. 16 plus 100 is 116. So the height at time t equals 1 is h of 1 that was 116 feet. Okay, question 4. This is from section 3.3, polynomial long division. So 2x cubed minus 5x squared plus 0x plus 1. Remember, we have to have that placeholder if there's any missing terms is going to be divided by x squared. I'm going to put a 0x here minus 3. Okay, x squared goes into 2x cubed, 2x times, multiply the 2x throughout this polynomial. It's going to give us 2x cubed plus 0x squared minus 6x. Now we subtract. Negative 5x minus nothing is negative 5x squared, and then 0, and these two negative signs here make a positive, so it's really plus 6x is positive 6x plus 1. Now the process continues. X squared into negative 5x squared is negative 5. Negative 5 multiplied through that polynomial there is negative 5x squared plus 0x plus 15. Now we're going to subtract. So that cancels. We get 6x, and that's going to be a minus 14 because it's really 1 minus 15 there. Now, this becomes our remainder. We talked about in this in class. This has a lower degree than this. So So that's our remainder. So the quotient is 2x minus 5, and then we have a remainder of 6x minus 14 over x squared minus 3. Okay, question 5 is also from section 3.3. Primarily what is meant to have you practice here is the remainder theorem. So when it says evaluate p of x at x equals 4, it's asking you to find p of 4, but not by plugging 4 in for all of these x's. We talked about that the synthetic division and remainder theorem can help us evaluate functions. So first we're going to evaluate or divide using synthetic division. There aren't any missing terms, so we don't need any zeros for any of the missing terms there. So we got a remainder of 0, which actually proves a couple of things. It proves that x minus 4 is a factor of the original polynomial because we have a remainder of 0, but it also proves that if we plugged 4 into the function, the remainder tells us the value of that function at this particular x value. So we can say that p of 4 is equal to 0. If this were a testing situation, if it says evaluate p of x at x equals 4, or if it says find p of 4 using the remainder theorem, this work has to be shown, otherwise you cannot get credit for the problem. Okay, question 6, this is from section 3.4. We need to find all possible rational zeros using the rational zero theorem. That's our p divided by q. Factors of p, remember, are here. Factors of q come from the leading coefficient. So 6 divided by 1 is just going to be 6. So we need factors of 6, which are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. That's a list of possible rational zeros. So factoring the polynomial means actually finding the zeros and writing the factors. So we need to choose from the list of possible rational zeros. I'm going to choose 1. And something to consider in this one is there's a missing term of x squared, so we need to have 1 and then a 0 for the x squared. Negative 7, that's 6. Looks like we got lucky right off the bat. X equals 1 is a 0 because we got a remainder of 0. So I know that p of x equals x minus 1 times x squared plus x minus 6. That comes from here. And then that factors further. This quadratic factors into x plus 3, x minus 2. Remember though, these quadratic factors don't always factor so nicely. If they don't factor, then you need to use the quadratic formula. So this was the answer for part 1. This is the answer for part 2. Sketch the graph. Now that we know the zeros for x-intercepts, sketching the graph is going to be easier. We have a 0 at 2, 1 at negative 3, and a 0 at positive 1. The y-intercept is that value there at the end, 6. You find a y-intercept, remember, by letting all the x's equal 0. And since this is a third-degree polynomial, I know the left side is going down to negative infinity, and the right side is going up to positive infinity. And all of the zeros have a multiplicity 1, which means that the zeros or x-intercepts, the graph crosses through at each of them and doesn't bounce. So starting from the left, I know that the graph's going to cross through at that 0. And then I have a value of negative 2 and a value of negative 1 that I need to plug in. I'm going to plug in negative 1 to see where the graph is. It may be that the graph is up here. It might be that the graph is right there. So if you plug in a negative 1 for all the x's, here, and here, and here, we would get -1 minus 1, -2, -1 plus 3, which is +2, and then -1 minus 2, which is -3. So that's +12. So when x equals y -1, the graph is way up here at +12. So I know that it goes quite a bit higher than the y-intercept. Comes down through the y-axis at 6, crosses through there, and I know at some point it's got to come back up, but because there's only fraction or decimal values between 1 and 2, we need to plug those in. So this represents the point 1, 12. Okay, part B is going to start same way. We need a list of possible rational zeros. So we have our factors of P and our factors of Q. 8 divided by 1 is 8. So 1, 2, 4, and 8. So let's see if we try 1. All right, well, I like this. This is easy. I'm getting it right on the first time every time. So x equals 1. What we have, though, at this point, if we were to write p of x in partially factored form, we have x minus 1, and then the remaining factor, where the reduced polynomial is x to the third plus 5x squared plus 2x minus 8. Since this isn't quadratic, we need to go back and choose again from the list of possible rational zeros and continue synthetic division to find another zero. So I'm going to do -1, but synthetic division on the reduced polynomial now. Okay, it doesn't look like it's -1. Try 2. Okay, it's not 2. Let's try -2. Okay, perfect. So now we know p of x is still x minus 1 is one of the factors. Now we know that x plus 2 is another factor, and then these represent the coefficients of a quadratic factor, x squared plus 3x minus 4. And then that can be, that quadratic factor can factor into x minus 4 times, let's see, nope, x plus 4 rather, sorry, x plus 4 and x minus 1. So looks like if we rewrote that, since we have x minus 1 twice, it would be x minus 1 squared times x plus 2 times x plus 4. So this is part 1, part 2, part 3. We have a 0 at +1, -2, and -4, and then a y-intercept at 8, at x equals 8. And since this is a 4th degree polynomial, the end behavior is left side goes up to infinity, right side goes up to infinity. And there's a couple of integer values here of, let's see, -3, -1 that we're going to need to plug in to figure out where the graph is. So at negative 3, we're going to have negative 3 minus 1 is negative 4 times negative 1 times 1 times negative 4. So that's negative 16. That's a bit off of the graph. So negative 3, I'm just going to mark it, is way down here. Negative 3, negative 16. At negative 1, negative 1 minus 1 is negative 2. Negative 1 plus 2 is 1. Negative 1 plus 4 is 3. Negative 1 minus 1 is negative 2. So let's see, that is 12. So negative 1 comma 12. Right up here. Negative 1 comma 12. So it crosses through at negative 4 because that has a multiplicity 1, or multiplicity that's odd. It comes all the way down at negative 3 comma 16. Comes back up. It crosses through at negative 2 because that has a multiplicity that's odd. Comes all the way up to negative 1 comma 12. Comes back down through the y-axis. Comes down to this 0, and it bounces at x equals 1 because it has a multiplicity that's even. Bounces off. Okay, question 7. Find a polynomial. It's got to be degree 3. So we need to have 3 zeros. X equals 1, x equals 3 minus 4i. And we talked about this in class. This is a complex or non-real 0. They always come in pairs, called the conjugate pair. So we know that 3 plus 4i is the other 0. So writing it first in factored form, like that. And then I would multiply these two together first using distributive properties, so x times x, and then x times negative 3, and x times negative 4i, and then negative 3 times x, negative 3 times negative 3, and negative 3 times negative 4i, and then 4i times x, then 4i times negative 3, and then 4i times negative 4i is negative 16i squared. So the negative 4ix, positive 4ix, 12i, negative 12i. And we talked about this also in class from section 3.5. I squared is negative 1, and negative 1 times negative 16 is positive 16. So combining like terms, we have x squared minus 6x plus 25 after multiplying those two non-real factors, or factors containing the non-real units, and then that's going to be multiplied with x minus 1. So then again, the distributive property is x cubed minus 6x squared plus 25x minus x squared plus 6x minus 25 is x cubed minus 7x squared plus 31x minus 25. Okay. Find all the zeros. First thing would be the possible rational zeros. And then testing them. And there aren't any missing terms of that polynomial, so just use synthetic division. So we have Right off the bat, another 0 found. X minus 1 times x squared minus 2x plus 2. Now, unfortunately, this doesn't factor. X squared minus 2x plus 2 doesn't factor, so we need to use the quadratic formula. I'm not going to sing it here on the video, but in class we learned a catchy little tune that goes along with this to help you remember. But anyway, opposite of b is positive 2. Then b squared would be negative 2 squared is 4, minus 4 times a times c over 2a. So this is 4 minus 8, which is negative 4 over 2. Square root of negative 4 is 2i, so this is 2 plus or minus 2i all over 2, which is 1 plus or minus I. All it says is to find zeros. It doesn't say to factor or to graph, so the end result will be listing all the zeros, x equals 1 and x equals 1 plus or minus I. Okay, part B, I'm going to start similar with a list of possible rational zeros. So we have 1, so we've got 52, and they're all going to, the factors of 52 are all going to be divided by 1, so it's really just the factors of 52. So it's 1, 2, let's see, 4 doesn't, 5 doesn't. So let's see, let's try 6. 6 does not. 7 does not. 8 does not. It might just be these. Let's see, 52. Yeah, 26. Okay. From this list, start testing using synthetic division to get a remainder of 0. There aren't any missing terms in the polynomial. Okay, so it's not 1. Try negative 1. Okay, so we found one. So since negative 1 is a 0, that means x plus 1 is the factor. These would be the coefficients of a third degree polynomial. We can't use quadratic formula and we can't factor it, so we need to go back to the list of possible zeros and continue testing on that reduced polynomial. Okay, so we found another one. So negative 1 is still a 0. 2 is a 0, which means that x minus 2 is the factor, and then the quadratic factor from those coefficients is x squared minus 2x plus 26. Okay, that does not factor either, so we need the quadratic formula. The opposite of b is positive 2 plus or minus b squared, so that's 4 minus 4 times a times c over 2a. 4 minus 4 times 26. So 4 times 26 is 104. 4 minus 104 is negative 100. Square root of negative 100 is 10i. So this is 1 plus or minus 5i. So the zeros are x equals negative 1, x equals 2, and 1 plus or minus 5i. Question 9. For part A, the intercepts, if I solve this equation and let y equal 0, then what we're really solving is this equation, x minus 2 equals 0. X minus 2 equals 0 when x equals 2. So the x-intercept is 2. To find the y-intercept, we let all the x's equal 0. So we get negative 2 over negative 2, which is positive 1. And then the asymptotes, vertical asymptotes, are going to come from factored form here in the denominator. So the domain restrictions are going to be negative 2, x cannot equal negative 2, and x cannot be positive 1. Okay, the horizontal asymptote, if we compare, this is degree 1, this is degree 2. Talked about this in class. If the denominator has a higher degree, then the horizontal asymptote is y equals 0 for the x-axis. Okay. Now, starting on the left side here, now two choices here. The graph can look like this, or the graph can look like that. Can't be both because it wouldn't pass a vertical line test. So I'm going to test a point. I'm going to test negative 3. See where the graph is at x equals negative 3. If I plug that in for all the x's here, I'm going to get negative 3 minus 2, which is negative 5. Negative 3 plus 2, which is negative 1. Negative 3 minus 1 is negative 4. Negative 1 times negative 4 is 4. So negative 5/4 is a negative value. It's just slightly lower than negative 1. So about right here. So that tells me that piece of the graph looks like that. Now, this right side is kind of atypical. And here's what I mean. To say that, well, either the graph looks like this or the graph looks like this would be incorrect because we have that 0 right here. So the graph is going to cross through the x-axis right there. And remember the behavior of a function as it nears a vertical asymptote. Either the graph goes up to infinity like that, or it can come down from below and look like that. The question is what happens to the other side of it, because if you recall our discussion in class, the whole reason for a horizontal asymptote is to model the end behavior of the function. So way out here, as x heads towards positive infinity, the graph is either going to approach the horizontal asymptote from above. In this case, the graph would look like that, or other way around, the graph could approach the horizontal asymptote to infinity and could approach the horizontal asymptote from underneath, like that. Like I said, this is atypical, but also something to be aware of. So what we need to do is, knowing that there is a 0 right there at x equals 2, let's plug in a couple other points to see where the graph is after that 0. So when x equals 3, we get 3 minus 2, it's 1. 3 plus 2 is 5. 3 minus 1 is 2. So 1/10, which is like that. When x equals 4, 4 minus 2 is 2, 4 plus 2 is 6, 4 minus 1 is 3, 2/18. So it's also a very small value. So it looks like what's happening here is it's coming down to negative infinity and then approaches the horizontal asymptote from above. In between these two vertical asymptotes in this region here, there aren't any zeros, and we know that there's a y-intercept here, so we can't have anything like this because there aren't any x-intercepts. We can't have anything like that because there aren't any x-intercepts. It can't look like that because there's not an x-intercept there. But what ends up happening is it looks something like this, and you can verify that if you wanted by plugging in a -1, for example. So -1 minus 2, that's -3. -1 plus 2 is 1. -1 minus 1 is -2. So -3 divided by -2, that's 1.5. So -1 comma 1.5 would be here. If you tested, it would be a little more challenging, but 0.5 would be right there. If you tested that, it would be up about right there. So the middle piece is a parabolic in shape right there. Part B, if we factor the denominator, we factor out an x and have x minus 3. If we factored in the numerator, let's see, we'd have 2x, and then we would need, let's see, a plus 3 and minus 1. Doesn't give us what we need. That doesn't quite do it. So let's try minus 1 and a plus 3. Yeah, that'll do it. Okay. So the intercepts first. The x-intercepts, remember, are letting y equal 0 or f of x. And a fraction is only ever going to equal 0 when the numerator is equal to 0. And that, so to solve that equation, we're going to get x equals 1 right there, and x equals -3/2, which is -1.5. The y-intercept, to find the y-intercept, we let x equal 0. So if all of these x's were 0, we end up with 0 minus 0 in the denominator. We can't divide by 0. Can't have 0 in the denominator, so it tells us that there aren't any y-intercepts. There's no y-intercepts. So we move on to asymptotes. Those are the domain restrictions. So x can't be 0, and x can't be 3, so we have a vertical asymptote at 0, which is another reason why we can't have a y-intercept, because there's a vertical asymptote on the y-axis. We have one at 3. The horizontal asymptote, if we compare, they have the same degree. The numerator and denominator have the same degree, so we divide leading coefficients. 2 divided by 1 is 2. So there's a horizontal asymptote at 2. Okay. Now the left part of this right here, I know there's a point right here already, which tells me that this piece of the graph is going to look like that. Skipping the middle piece for a second, going over here to the right, we can either say that there's a piece of the graph up here, or we can say that there's a piece of the graph down here. Now that last one can't happen because there's no x-intercept right there. So because there's no x-intercept, that tells me that this portion of the graph is up there in that corner. Now in between the two x-intercepts in this region here, I'm going to go ahead and plug in x equals 2 to figure out where that point is as it nears that asymptote of x equals 3. So when x equals 2, plugging that in to the function here, we're going to have 2 times 2 here, that's 4. 4 plus 3 is 7. And then 2 minus 1 is 1. 7 times 1, so that's 7. And then 2 times 2 minus 3, that's negative 1. 2 times negative 1 is negative 2. 7 divided by negative 2, that's negative 3.5. So when x was 2, we were down at negative 3.5 right here. So that tells me that the graph is approaching negative infinity, and it crosses through that 0 right there because that had a multiplicity that's odd from that 0, from that factor. So then it crosses through and heads up to positive infinity right there. All right. Question 10. These are sketching polynomial functions from section 3.2. It's already in factored form. So we find the zeros of x equals 0, x equals 2 with a multiplicity of 2, and x equals negative 2. So we have 0, 2, and negative 2. So the first step is to find and list your x-intercepts. Y-intercept you find by letting all the x's equal 0. So we have 0 times this times this. 0 times anything is going to be 0. And we can already tell here anyway we had an x-intercept of 0, which serves as the y-intercept as well. So there's your y-intercept. Now the degree is a little bit harder to spot just by looking at it because it's in factored form. But if you consider the multiplicities of each factor, this is multiplicity 1, this is multiplicity 2, that's multiplicity 1. If you add up all the multiplicities of each factor, you come up with the degree. It's degree 4. Degree 4 polynomial with a positive leading coefficient means the left side is going up to positive infinity, and the right side is going up to positive infinity. Now connecting these two sides, this 0 of negative 2 comes from that factor. That factor has a multiplicity that's odd, multiplicity of 1, so it crosses through. Now, at negative 1, we need to figure out how low this graph goes because it's an integer value. So we have negative 1. Plugging in negative 1 for all the x's. Negative 1 minus 1 is negative 3. Negative 3 squared is 9. And then negative 1 plus 2 is 1. So it goes all the way down to negative 9. Comes up, crosses through there because that 0 of x equals 0 comes from that factor right there of x. That factor has a multiplicity that's odd, so I know it crosses through. And then I need to figure out how high it goes before it comes back down, so I'm going to plug in x equals 1. So 1, and then 1 minus 2 is negative 1. Negative 1 squared is 1. 1 plus 2 is 3. 1 times 1 times 3 is 3, so it goes up to 1 comma 3. Now it bounces there because it comes from this factor, which has a multiplicity that's even. So it bounces off that, comes up there. For part B, we have a 0 of x equals 1, and another one of x equals negative 2. To find the y-intercept, we plug in zeros for all the x's. So we have negative 1, and then 2 squared is 4. So the y-intercept is negative 4. The degree of this, if we added the multiplicities, this has multiplicity 1, multiplicity 2, 1 plus 2 is 3. So this is a third degree polynomial with a positive leading coefficient. So that tells me the left side is going down. right side's going up. So now to connect these two, at -2, it's going to bounce because it has an even multiplicity. So I know that it's going to bounce there. And then at -1, we need to figure out where the graph is or where the function is at -1. So if I plug in -1 for the x's, I'm going to have -1 minus 1 is -2. -1 plus 2 is 1. 1 squared is 1. So -2 times 1 is -2. So it goes through -2, comes to the y-intercept, crosses through there because that has an odd multiplicity, x minus 1 to the first power. So it crosses through, meets up there.